Welcome to the recording of the Pacific Institute for Climate Solutions panel event, The Next Frontier, Negative Emissions Technologies, Contribution to Climate Solutions. PICS is hosted at University of Victoria, and so we acknowledge with respect the Lekwungen peoples on whose traditional territory the university stands, and the Songhees, Esquimalt, and Wet'suwet'en peoples whose historical relationships with the land continue to this day. We now join our Executive Director, Sybil Seitzinger, who is giving an introduction to PICS.
We're a collaboration across the 4 major research universities here in British Columbia, and we engage with users. We call them solution seekers to advance new knowledge for climate solutions. That's very consistent with, of course, with our mandate, which is to develop impactful evidence-based climate change solutions through collaborative partnerships, which connect private and public sector solution seekers with experts from the universities. So how do we do that? Well, we do that what we call it the PICS way, which is to combine solution seekers or bring solution seekers to the table. Those solution seekers can be from any level of government, from the private sector, from communities, from First Nations. They come with their questions. They're questions that need research in order to get information that they need to make decisions on climate solutions, climate action. So we bring them together with the research partners from the universities, not only the 4 PICS universities, but beyond as well. And where that intersection is where we see PICS. Where do those 2 groups come together to work together in a collaborative way to advance new knowledge for climate solutions that lead to climate action? The range of topics is quite broad, of course, because that is what's needed for climate solutions, all the way from energy to the built environment to policy. And not only mitigation in those arenas, but also, of course, very importantly, adaptation and resiliency. The newest area in which we've developed projects is in negative emissions, the topic of this event today. I want to give you just a couple of examples of negative emission technology projects that we've been funding. Forests. Forests remove CO2 from the atmosphere, as we know, creating new biomass. But also, as has been very evident, not only in the past, but just in the past few weeks, is that climate change is causing increased frequency and severity of wildfires with significant consequences for the forest carbon balances. But this project aims to develop strategies to reduce emissions from wildfires, to enhance forest carbon sinks, and to stimulate new bioeconomy opportunities for forest fiber. Another project, Solid Carbon, is developing an offshore negative emissions technology that aims to turn captured CO2 into rock by injecting it into ocean sub-seafloor basalt, where it will mineralize and remain permanently stored. This net aims to put, as we say, carbon back where it belongs, in the ground. So our programs are aimed at driving partnerships and engagement, helping solution seekers become solution makers. We do this in a very collaborative co-design, co-development, co-delivery approach. And we have research programs, we have internships, we have partnerships of various sorts. And I encourage you all to sign up, if you haven't already, for our mailing list to find out about PICS opportunities, both in research as well as events and more. And thank you all for attending, what I think is going to be a very engaging and exciting panel discussion coming up now. So with that, I'll turn it over to Devin Todd, our researcher in residence for negative emission technologies at PICS, who is really the mastermind behind this event tonight. So over to you, Devin.
Thank you, Sybil, for the introduction. Thank you, everybody, for joining us at today's event. What I'd like to do is just give a quick, brief review of the plan today. We're going to start with a brief introduction to NETS that I'll provide. We'll have some opening remarks from our panelists. There'll be a period of Q&A and panel discussion. We'll close off with some closing remarks, and then we'll wrap up. I'd also like to draw your attention to the Q&A feature on Zoom. That's going to be the Q&A button in the lower bar. Already we've had some questions about recording of the presentation, and will we have slides available. We are planning to provide a recording of the presentation that we will post to the PICS website, but I strongly suggest participating throughout the entire event because that's the best way to get live questions incorporated into the program. So with that, I'll just start talking about nets. Why are we here? So the impacts of climate change are apparent. If 2020 was not enough already, we have even more to look forward to. On the global scale, we can consider increased extreme weather events, food and water insecurity, social instability and upheaval, habitat degradation and loss of biodiversity, and more. In Canada in particular, we can also highlight forest fires and pests, flooding and dam failures, sea level rise and storm surge, and a large Arctic of thawing permafrost. Why we're here is because we need mitigation and adaptation solutions to climate change. So what are we trying to aim at? Well, the IPCC target, the Paris Accord, is keep warming below 2 degrees Celsius, ideally even better at less than 1.5 degrees Celsius. However, our nationally determined contributions, at least in Canada for 2030, have limited ambition. We can expect new NDCs to be posted soon. That's kind of what the schedule says, so we can stay tuned to that. But really, in 2030, we have maybe 9 years to act. That's a very small window, and it doesn't seem like we have a lot of impetus yet. Now, part of getting to our Paris targets is going to involve negative emissions technologies. And just to take a step back, we can consider greenhouse removal technologies as a whole, where typically we talk about carbon dioxide removal from the atmosphere. But I'd like to just mention that there are also other greenhouse gases that we can target, as well as other carbon reservoirs that we can target. If greenhouse gas removal or carbon dioxide removal is the outcome, then negative emissions technologies are really the means to get there. So what's a net? Nets are diverse, and they're defined by their shared outcome more than their implementation details. When considering what is and is not a net, it helps to keep a few questions in mind. The first one is, where is the carbon coming from? Where does the carbon end up? Is that a permanent solution? Is that going to escape? Was the action an intentional human effort? Was it additional? And just to circle back to the idea of permanency, to give some examples, we're talking about locking carbon away in vegetation, soil, rocks, geological reservoirs, or long-lived products. It's important to note that synthetic fuels or carbonated beverages don't really qualify. So where do nets fit? Nets situate in a broader set of climate solutions. What you see here is just one of the many ways to look at this space. It shouldn't be your only way. Considering the wider space, it's important to see that there are some overlapping conflicts and synergies between negative emissions and some of the other solutions of part of climate change, or climate solutions. For example, there are common ecosystem management toolboxes for land use purposes, or we can be powering carbon dioxide extraction machines with renewable energy. Because of these overlaps, and our panelists will speak to these ideas, I want to prime you to think about portfolios of climate solutions. I also invite you to reflect on your own thought processes for how you develop these portfolios. For example, we tend to account CO2 reductions and negative emissions as equivalent, not to mention the differences within nets. So speaking of differences between nets, if you ask an investment banker, I'm sorry if there are any in the room, for a selection criteria, you'll likely get, give me a market size and a profit indicator. That's already a huge simplification of the financials and the potentials for negative emissions. More importantly, it neglects critical technical, environmental, and social justice considerations. Our panelists will touch on these, so I'll give a few more framing considerations. Negative emissions resist simplification. Their co-benefits and concerns can be totally different types or share very different severities across different implementations. Answers can hinge on technology and project level assumptions. What works in one place might not work the same way in another. Lastly, uncertainty is everywhere. How confident can we be that a given net bet might actually pay off? Oops, and there's a bit of a delay. Sorry for that. All right. Well, some things maybe we can bet on. What we might bet on is an urgency for rapid growth. We're going to need very large cumulative annual growth rates if we're going to scale from, say, 1 million tons of CO2 per year to negative emissions on the order of gigatons of CO2 per year by 2050. Secondly, nets are often not free. Will we see new incentives or business as usual? Can we rely on corporate goodwill, market pull, or niche markets? And if not, then what might work? Finally, we are right now experiencing a period of upheaval. Consider the acute unrest around environmental and social concerns. Layer on populism and a global pandemic. Could we really have predicted this outcome? How can we anticipate future unknowns? And with that, I would like to introduce our speakers in order of presentation. So Kirsten Zickfield is a professor of climate science in the geography department at Simon Fraser University. Her research features Earth system modeling to explore the long-term effects of human activities on climate. She is a lead author of the IPCC Special Report on Global Warming of 1.5 degrees Celsius and is a lead author of the forthcoming Sixth Assessment Report. Jennifer Wilcox is a professor of chemical engineering and energy policy at the University of Pennsylvania and a senior fellow at the World Resources Institute. Her research explores energy and the environment, in particular technologies for CO2 capture, utilization, and sequestration. She is a committee member of the National Academy of Sciences and the American Physical Society, looking at carbon capture, and has authored the first textbook on the subject called Carbon Capture. Holly Jean Buck is a professor of environmental and sustainability at the University at Buffalo, teaching environmental justice. She is a geographer and environmental social scientist studying how emerging technologies could address environmental challenges. Her book, After Geoengineering, Climate Tragedy, Repair and Restoration, explores best case scenarios for carbon dioxide removal. Finally, Christopher Neidl is the co-founder of Open Air, a global volunteer network to advance direct air carbon capture through open source, crowd-based research and development and advocacy missions. He brings 15 years of experience in North American and international on and off-grid renewable energy. I won't spoil anything, but we can expect some cool stuff to come out of Open Air soon. And lastly, just one more reminder of where you will find the Q&A function at the bottom of the toolbar. So with that, I'm going to invite Kirsten, if you could please, I will stop my sharing now.
Okay, good, thank you. Thanks, Devin, for the introduction. So my slides should come up in a moment. There you go. Can you actually see them?
Yep, we see them.
Yeah.
Although
okay,
we see,
good.
you'll want to, okay. There we go.
Okay, good. All right. So as a climate scientist, I'm going to present an Earth systems perspective on nets. So what I'll do, I'll briefly motivate where the motivation behind looking into nets comes from. And then I'll very briefly talk about the sequestration potential, or I think, as Devin called it, the capacity of these technologies. And then I will finish with some Earth system considerations, so Earth system feedbacks that potentially could reduce the effectiveness of some of these nets. So I will start off with the concept of a carbon budget. So a carbon budget is the maximum amount of carbon dioxide that we can release into the atmosphere over all times. So this is very important to keep global warming below a given limit with a given probability. So let's say if we aim for 2 degrees or 1.5, then there's a finite amount of carbon dioxide that we can release into the atmosphere to stay below those limits with a given probability. And one illustration of this is a carbon bucket, which is shown here on the left, which is from the Global Carbon Project. So the carbon bucket illustrates this total amount of carbon that we can release. And what you see here is the amount to, or the extent to which the carbon bucket is already filled. So this is in 2019, and 9% of the carbon bucket is already filled, which means that the humankind has already exhausted 90% of the carbon budget to stay under 1.5 degrees. So here on the right-hand side are the numbers. So these are from the IPCC special report on the global warming of 1.5 degrees. And these numbers are from 2018. So we're currently emitting a little bit over 40 gigatons of carbon dioxide per year. 1 gigaton is 1 billion metric ton of carbon dioxide. So we have to subtract around 80 billion metric tons of CO2 per year from these numbers. So if we aim to limit warming to 1.5 degrees with a 66 probability, which means that our chances are 2 in 3 that we're actually going to stay under that limit, then we have a little bit over 420 left. Again, this is from 2018, so we have to subtract 80, so and we end up with 340. And so this is just 8 to 9 years of current global emission until we completely fill the bucket. And if we reduce our odds of limiting warming to 1.5 degrees, then the carbon budget is a little bit higher. But still, this illustrates how daunting the task of limiting global emissions to these carbon budget numbers. And for this reason, many of the emission pathways that are consistent with limiting warming to 1.5 degrees, they involve net negative carbon dioxide emissions in the second half of the 21st century. So what is shown here is a figure, again, from the IPCC special report on 1.5 degrees. And it shows the global total net CO2 emissions. So net are positive emissions into the atmosphere minus removals out of the atmosphere. And what this indicates that all emission pathways that are that were considered by the 1.5 degree report, they require some degree of net negative emissions after 2050. So really these negative emissions are key to achieving stringent climate targets. So I'm not going to spend, so there's a lot of detail on the slide here. I'm not going to spend a lot of time on this. So what this illustrates is the sequestration potential of land-based nets. So this is from a recent paper by Rowe et al. And it shows the sequestration potential for a range of land-based nets. And so the point here is to show that some of them actually have a considerable potential to store, to remove and store carbon dioxide. So if you look at the upper part of this diagram, so these light gray bars, then what you see here is a range which is from 1 to 20, from 1.5 to 36 gigatons of carbon dioxide equivalent per year, with the median, which is indicated by the star, of 11 gigatons of CO2e per year. And again, sort of just to put this into context, recall that we're emitting around 40 gigatons of CO2e per year. So this illustrates that if these things can scale up, they are they could play an important role in the mitigation portfolio. And some of these, a subset of these nets, which are mostly land-based and are often referred to as a natural climate solution or nature-based solution. So these are the more the ones that involve forest, soil carbon sequestration. So the ones that are less engineering related. They also have a number of co-benefits in terms of air, water, biodiversity if managed sustainably, and so on. So they are an interesting player in our mitigation portfolio. So now often, so there's a little bit of a disconnect between these, between the community that explores these negative emission technologies and the climate science community. And often these sequestration potentials are equated with the amount of carbon that is removed from the atmosphere. So there even was a science publication out there last summer that made that mistake. So some of you might know this Bastin et al. Paper that looked at the potential for global reforestation. So one point I would like to make here is that only a fraction of the CO2 sequestered by a net is actually removed from the atmosphere. And that fraction is about 50%. So let's say if we say that a certain plot of forest sequesters so many million tons of carbon dioxide, then if we translate this into a decrease in atmospheric carbon dioxide, then it's only about half of that. So why is this? So when we emit carbon into the atmosphere by burning fossil fuels, about half of that ends up in the ocean and in the land, and about half of that remains in the atmosphere. So conversely, if we remove carbon dioxide from the atmosphere, and now the atmospheric CO2, the concentration of carbon dioxide in the atmosphere is lower than in a reference case without carbon dioxide removal, then the ocean and the land, they return a certain fraction of carbon back to the atmosphere, which is also around 50%. And so the mechanism is the same that drives carbon into these things. It's just now operating in reverse. So the first thing to take into account that only half about of the carbon that is sequestered in a forest or in a soil is actually removed from the atmosphere. Something else that we need to take into account when looking at the effectiveness of nets is also that there are climate feedback that could enhance or then diminish the carbon sequestration of these nets. So if we have a very vivid example right now with forests burning all over the western US. So as the climate warms, aridity increases, temperature increase, disturbance regimes such as fires and pests might increase and diminish the carbon sequestration potential or affect the permanence of the sequestered carbon in forests. Also, there are other feedbacks, which we call biophysical feedbacks, that we need to take into account. So let's say if we reforest or afforest at high latitudes, then the reflectivity of the forest is actually lower than that of bare soil, especially during the winter when we have snow cover. And this again affects the climate benefit of afforestation, for example. And some of these nets, especially those that involve fertilizer use, involve co-emissions of other greenhouse gases, nitrous oxide, sometimes methane, or volatile or organic compounds, which then could reduce the effectiveness of these nets even further in terms of their climate mitigation potential. Okay, good. So yeah, so I leave it here for now and look forward to the discussion.
Thank you, Kirsten. So now we'll be moving on to Jennifer Wilcox.
Thank you.
Yep, we see the screen. Thank you. And just a reminder that we're going to want to try and keep things within reasonable time, and ideally we'll move to the discussion component in about say quarter of an hour, 20 minutes.
Okay. I'll try and move through. So thank you so much for tuning in and listening. So I wanted to start with this slide. If you haven't seen this yet, this is a report that was released by the National Academy of Sciences of Engineering and Medicine in early 2019. And so what this is we were charged as a committee to establish a research agenda for negative emissions technologies. And one of the major conclusions from this is actually very much consistent with what Kirsten just presented, in that in order to meet climate goals, we need to be able to remove 10 gigatons of CO2 per year by mid-century and up to 20 gigatons of CO2 per year by the century's end. And we looked at a number of technologies, and both natural-based solutions and also engineering solutions. But this table, what it's showing, and this is in the executive summary if you wanted to take a look at the details, and I'll just go through it quickly, is we wanted to see if we could add up to 10 gigatons with technologies that exist today under $100 per ton. And so when we did that, and this is also really consistent with what Kirsten presented, and so when we look at that, all of these solutions are really associated with nature-based options that are less than $100 per ton today. And a lot of the times when you think about additional technologies like mineralization or direct air capture, which I'm going to talk a little bit about today, those technologies don't really exist today at an interesting scale. And so they're still pretty expensive. And so what we were saying in our report is that from today until mid-century, we're probably going to rely on a lot of these nature-based solutions because they're affordable today. But it doesn't mean that we shouldn't invest in these other technologies today such that we can learn by doing, decrease costs such that they'll be more affordable in the second half of the century when we really are depending on all of the solutions to get to the scale that we need to. This is just a little bit of an overview picture of all of the different approaches that we considered, everything from coastal blue carbon to the accelerated chemical weathering of rocks. And so in the Earth's crust, there's a lot of rocks that are either comprised of calcium or magnesium, and that those alkaline feedstocks are reactive to CO2. And so that's one method of bringing CO2 out of the atmosphere. I'll talk about direct air capture a little bit more detail. Bioenergy coupled to carbon capture and storage is another opportunity. And then, as Kirsten mentioned, afforestation, reforestation, and then soil carbon storage. And so in the report, we took a deep dive into all of these sectors and really looked at a research agenda associated with them. Another report that was interesting too, and along these lines, was a report that was released out of Lawrence Livermore National Labs. And it was focused on the path required for the state of California if they want to reach carbon neutrality by 2045. And so a big take-home message of this report, which also will be related to a lot of similar reports. Hopefully we have another 49 of them coming out in the United States because we need them. But a big push towards the conclusions was that in order to get to neutral, there needs to be some component of carbon removal. That's because there are sectors that are just very difficult to avoid today, whether it's agriculture, transportation, or industry. And so carbon removal plays a role in dealing with those very difficult to avoid emissions. So what is direct air capture? So direct air capture is a way to use chemicals in order to remove CO2 from the atmosphere. Some of the pros are it has the potential to be a negative emissions technology or carbon removal. It's a method for dealing with those difficult to avoid emissions. It doesn't require arable land. So you're not competing with food like you might be for biomass related energy. And then the cons, energy inputs are very significant. So this is a very energy intensive process. It's always going to be cheaper and easier to just avoid carbon emissions in the first place. And direct air capture should never be seen as a replacement for just point source capture if the opportunity exists. The other aspect is that the land footprint is pretty significant as well. So just a quick look here at the energy. I know that this is a plot based upon the combined first and second laws of thermodynamics. I can't help it. I'm a chemical engineer by training. But the point in this is that there's a minimum amount of work that's required in order to do a gas separation. So whether it's taking CO2 out of the exhaust of a power plant or taking CO2 out of the atmosphere, we can actually calculate the best we can do. It's the minimum thermodynamic work. And when you do this, you can actually pretty quickly see that the energy required to take CO2 out of the air compared to the exhaust of a power plant, in this case, about 3 times as great. And then in terms of the actual contact area, because of the dilution of CO2 in the atmosphere, could be up to 300 times more significant. And so what those translate to directly is the operating expenses in terms of the increased energy, and also, you know, the contactor, the surface area, and the capital costs of actually building the contactor. And then I just want to show some pictures. And so this is a picture of what a carbon capture process would look like at a power plant. And so what you see here is this big, tall, thin tower. And the idea is that the gas is coming at the bottom, and each one of these horizontal lines is really an opportunity for the CO2 in the gas phase to interact with a chemical. And once it interacts with that chemical and reacts, it's captured. And so as the gas moves up this column, it becomes cleaner and cleaner of CO2. And as the solvent or the chemicals are coming down, they're becoming more and more saturated in CO2. And so you notice here that if we wanted to capture all the CO2 in a given stream, we'd have to have an infinitely tall tower. We wouldn't do that, it's too expensive. And what I want to point out here is that although we have all of these technologies too that exist today for point source capture, we also have them for direct air capture, but they look very different. And so what I'm showing here is just a different type of contactor. For direct air capture, because you have that dilute concentration in the atmosphere, your surface area for the contacting is going to be significantly higher. The other thing that's interesting is the depth. So before we had tall and thin, and here we kind of have this, you know, narrow depth. And the reason for that is because you want to minimize the energy. And what you have to do is you have fan powers, because air on average moves about 1.5 meters per second. And you want to be able to push it through. So you need to overcome that, it's called pressure drop. So you need to be able to push the air through. And the deeper the bed, the more carbon you capture, but the deeper the bed is the more energy that you're spending. And what typically goes inside these contactors, there's 2 leading technologies today. One is a solvent-based approach, and it's actually close to home for those of you that are in Canada, because it's out of British Columbia, called Carbon Engineering. And they have these structured packings that fit inside the contactors. Another technology is based upon solid sorbents. This doesn't look that different from the catalytic converter in your automobile. They're very different. Solid sorbents, you might have heard of the company called Climeworks. And so this is the type of technology that they have. They shouldn't be treated equal. This one requires some water. This one is a net producer of water. They both have different land requirements. They both have different energy requirements. This requires a temperature of 900 degrees C heat. This one requires 100 degrees C heat. And so they're both very unique technologies with different applications. This one is cost effective at a scale of 1 million tons of CO2 removal per year. This one is actually modular and can scale down or scale up. So each one is very unique and different. And this is just going up to the energy required to actually do it. So if you were to think about 1 million tons of CO2 per year from the atmosphere requires a power plant. And you have to think carefully. It's not just about the design of the direct air capture plant, but what's the design of the power plant that's going to couple to it. If you rely on fossil fuels, you're only just emitting that carbon back into the atmosphere. So the best approach really is looking at decarbonize energy resources to couple to direct air capture. Finally, I'm just going to show a little bit of a deep dive from the California report. This is a chapter that I co-authored. And this is based upon the solid sorbent-based approach, where they only require 100 degrees C heat. What that means is that you can couple to waste heat, you can couple to geothermal energy. There are a lot of opportunities for doing that. And so what we did is we looked at all of those types of opportunities in the state of California. And for an nth of a kind plant, which isn't today yet, I think they have 15 projects globally. But for nth of a kind plants, we can actually get the cost down to roughly $200 or less through these different strategies. And the reason why is you're piggybacking on top of energy infrastructure that already exists. So you're decreasing the capital expense by doing that. I'll end with this final slide, which is, it used to be the story of mitigation was all about avoiding carbon emissions. And I want to emphasize that, of course, we have to do that first and foremost, and carbon removal shouldn't be seen as a replacement to doing that. But now we've run out of time, and there's an urgency, and that it's not going to be enough. And so the new portfolio is looking at all of these things, which include the removal of CO2 from the atmosphere. And I'll hand it off to our next speaker.
Thank you, Jen. Sorry, so we're going to have Holly Jean Buck join us next. And yeah, so we can see some of those ideas about portfolios and going back to what Kirsten presented, the scales of negative emissions that we're going to be needing.
Sorry, I'm trying to figure out how to not share here.
At the top of the screen, there'll be a green bar, and there should be some sort of, it may have to, you know what? It's okay. Holly, could I please ask you to share your screen, and that should override.
I think you can override me.
All right. How's that looking?
Great.
Good.
Yep. You'll want to.
Thanks to all of you for taking the time this evening to think with us about this. You know, many of us have many Zooms throughout the day, so it's really a testament to your passion for climate action that you would voluntarily engage in one more. I'm really happy to talk about this question of whether can scaling up negative emissions technologies be compatible with environmental justice. And broadly, how do we balance scaling up negative emissions with our other goals, not just our other climate goals, but our other sustainable development goals, ecological goals. And I want to invite you to imagine what it's like to be standing in a world that achieves this scenario, somewhere down near the end of the century where that red dot is, and we're on the threshold of net negative. So what kind of landscape are you looking at? What do you do for work? Are you part of a community? I mean, what's going on in that world? There's obviously infinite possibilities for the details of that. But I want to talk about 4 possibilities. The first one being that you could have a system of scaled up nets. We've reached that point. But it's bad for biodiversity. It's bad for our social justice aims. Maybe the configuration of all that energy needed to power direct air capture is not optimal for communities and for biodiversity. Maybe carbon removal jobs end up being low-wage labor or highly gendered labor, much like the fossil fuel industry today, substituting that out where men have high-paid positions in the community and women are doing low-paid service jobs, and the attendant social dynamics of that. Maybe the overall cost of the carbon removal is borne by working classes. Then you could have another world that doesn't reach that picture, right? What it has is scaled up nets, the effort and the appearance of nets without the actual climate significant goals. Maybe CO2 coupled with enhanced oil recovery fails to be the bridge that some hope it will be. Maybe there's incorrect or falsified accounting with that or with other methods. Basically, the appearance of negative emissions for a while, but at some point in mid-century, it's realized that actually the climate impact we hope for isn't happening. Another possibility is that the world knows how to remove carbon, all the things that Jennifer and Kristen just presented, like it's there, but negative emission technologies end up being rejected. Either they could be branded a false solution and their reputation is tainted by climate grifters, or they're seen as too expensive. I mean, there's other possibilities there, but a decision not to pursue all the things we've just heard about. And that could result in climate impacts being worse than they could have been if we had developed negative emissions technologies, with people of color, women, people in the global south disproportionately suffering those climate impacts. The fourth world, which I really hope that we can work towards together, is that negative emissions grow up with social and environmental justice goals. So carbon removal jobs that are good jobs and available to everybody. Carbon removal projects that are redirecting funds and investment to rural communities and environmental justice communities. The policy design for carbon removal ensuring the costs are borne by those who can afford it. Just to say a few, I mean, there's a lot to say here about what a just transition really means and what how carbon removal fits into that. So I'm gonna end with a brief framework. These are really initial starting points. What we need is communities to be developing frameworks, and they might look different than this one. But thinking about these different dimensions of environmental justice. So carbon removal through an EJ lens, procedural dimensions at the table, who's there in the design phase of the technologies, not just being consulted on them after they've been innovated. Distributive justice, not just who bears the harms from living perhaps nearby a facility, but who reaps the benefits from it. Reparative justice, so are the penalties and restorative measures for past damages fair, right? Do the same fossil fuel companies who polluted get to go bankrupt, spin off toxic assets like old oil wells into other companies, and then have an arm that continues to profit from standing up a carbon removal industry while failing to clean up the old wells? I mean, those are real world questions. Intergenerational, so what obligations are our policies and technologies placing on future generations? And recognitive justice is maybe one of the more challenging ones. How do we recognize the values and cultures and situations of places and peoples that are affected by scaling up these new industries and approaches? It's challenging because the values aren't stable or straightforward or universal, but they need to be part of the conversation. And this isn't just like a normative, it would be nice to have this. I think this is actually necessary for carbon removal to scale up, just because of the size and the cost of it requires a huge social buy-in. So thanks for listening. I look forward to our discussion.
Thank you, Holly, and thank you for ending on that World 4 on a slightly brighter note. So next up, we're going to have Chris, and I see that, yeah, that all seems to be working. So I'll let you take it from there.
Great. Well, thank you so much. Truly honored to be here. So what I want to just sort of put forward is an idea of how do we achieve nets, or how do we achieve a carbon negative future? And what I'm particularly interested in is how does this parallel evolution over the last 25 years since the internet born of creating new modes of production focused around distributed voluntary networks potentially help get us there? How does this one mission intersect with this other historic development? And specifically focusing on direct air carbon capture, I'm lucky that one of the world's leading thinkers in direct air capture preceded me. So now you know what direct air capture, or as we call it, direct air carbon capture, which we think is a little bit more descriptive, what it is. And Professor Wilcox also laid out the huge challenges that we face in order to really scale this up so that it can play a meaningful role in the climate crisis. So we need to obviously have many different areas of R&D that we need to accelerate development in. We need to radically reduce both the financial and the energy costs of direct air capture. And we need to integrate direct air capture into markets. We need to be able to sell the services that DAC provides. And we need to do it very, very quickly. And our typical way in economics of thinking about how are we going to get there, what's the innovation model, usually has centrally firms participating in markets. And they're incentivized to deliver these carbon removal services. And to the extent that markets don't provide that incentive, the government intervenes, creates a regulatory environment, corrects for market failures, invests in public goods, and that should take us there. So this is sort of the waiting for Elon Musk type of model. And I don't think that that's adequate or that's enough. And I think that what interests me about networks is the efficacy that we're seeing developing in mostly online, distributed, volunteer-based networks. And many of you, all of us, are familiar with what I'm talking about here. What might come to mind is open source development, which is one of the oldest distributed production modes that came out of the internet, initially focused around software. The crowd in general, when we're referring to the crowd, that's certainly related to this universe of modes, crowdfunding and crowdsourcing. The term that I like the most and that I sort of aspire to, I guess, for our project is peer production or commons-based peer production. This is a term that was initially introduced by a network scholar named Yochai Benkler. And what we're describing here is it's a model for economic production in which the creative energy of large numbers of people is coordinated, almost always through the internet, into large, meaningful projects, mostly without traditional hierarchical organization or financial compensation. And in particular, just to kind of pull out a couple of the features of peer production that I think are most relevant and could be most impactful, is this whole part about without traditional hierarchical organization and without financial compensation, which are the most radically different from our traditional innovation models. For one, at the center of peer production is volunteerism and amateurism. And this isn't this sort of early phase that we work through until we become an organization. And it's not something that supports staff or professionals. This is always at the center of it. It's the creativity and the contribution of the volunteer or the amateur who's participating because they're intrinsically motivated to do so. And you can do enormous amounts of power and creativity can be harnessed through this. And in fact, when you introduce financial compensation into volunteer networks, you tend to get less effective and less creative networks. The other thing that we really need to pay attention to with networks is that scale really matters and diversity really matters. The efficacy of a network is a function of not only how many different people are participating in it, but the diversity of where they're coming from, their context, their experience, their fields. And there's study after study that this is sometimes not stressed with diversity. It's a value in its own right, but it's also, it leads to better results when you're creating things. And so when we think of networks, it's not necessarily the case that we're talking about this is a total divergence from our firm and market-based reality. In fact, they can and often do go hand in hand. And in fact, it's the network, the distributed volunteer network, which I think of as the sort of creative primordial ooze that is particularly good at generating new ideas, experimentation, and innovation, sort of productifying or coming up with new ways of thinking. And that can inform markets as well, and the outcomes of markets. And so I'm not talking too abstractly here, we're all familiar already with peer production, with productive networks. The free and open source software that powers so many of our personal technologies emerge from open source. Wikipedia, which we use every day. Crowdfunding is obviously related to this, bringing in vast amounts of resources, both for investment and for lending and for charitable purposes. Open hardware and maker culture is not just kind of cute tinkering. It's given rise to some of the most high impact technologies of the future, like 3D printing and Internet of Things. Citizen science, something I do with my son every day, eBirding. eBirding is the largest citizen science project. It's also a big data repository entirely provided by volunteers that tracks the migrations and populations of birds all over the world. And then certainly most of us have heard by this point of cheap gene editing software like CRISPR and the type of movements around biohacking that is inspired. What's really interesting to me as well is that it's also very much showing up and imprinting and being printed by advocacy and activism. I would say particularly across the spectrum, but particularly on the progressive end of the spectrum. We see organizing has always been about networks and informality, but we're seeing a greater sort of synergy and convergence between online networks and activist modes. And in fact, regardless of what you think about these political movements, there's no doubting that these movements, which are particularly distributed in nature, decentralized, a lot occur or enabled by online interaction, have made enormous impacts on our politics and on our society, and will continue to do so. So what we're exploring with our project at Open Air is how do we bring to bear those powers on the needs of direct air carbon capture? How do we drive down costs? How do we create markets? And that is the question that we started with just a little over a year ago. Can a distributed volunteer network really play a role in scaling DAC up? And we think that in some ways it's sort of a perfect candidate for an open network-based project. One is you have all of those people. It's an enormous constituency of concern that's incredibly diverse, that cares about climate change and wants to do things about it. And then with direct air capture, you have it's a critical solution now that's being recognized as a critical solution. The bugs, as we would say, the problems or challenges are relatively well defined. So the creativity of the crowd can be very focused narrowly on particular challenges. And it's also an undefined sector right now. It hasn't been sort of defined by the market or by corporations or by particular firms. It's sort of a wild west, which allows people to participate and really take it in different types of directions. And just to close, Open Air over the last year, there's two domains that we really operate within. We are building network communities around R&D missions focused on DAC, but importantly, I come from the solar background, policy. The policy environment that needs to be put in place in order to enable DAC scale up. And our missions currently, one right now, which I was hoping I could announce the launch of, we're probably still a couple of weeks away, it'll be the first miniature open source direct air carbon capture machine that will be licensed under an open source license. And our project there is to develop a community globally to apply our collective intelligence on technical issues that face DAC, but to also think of new types of applications. It's miniature for a reason, because that allows people to build it. But I believe in addition to the plant scale type of applications that Professor Wilcox laid out, a key to the creative evolution of DAC will be its miniaturization and the ability to not only set it up as a plant, but to embed it as a feature of things, buildings, et cetera. And then the other area that we're having a lot of action in is in the policy area. In New York State, we have, through a collaborative effort, introduced legislation that's focused on concrete procurement of concrete by the state that includes the utilization of carbon, which can come from industrial sources or for DAC. Not only have we gotten this advanced in the legislature, and it's gaining some really significant momentum, it's also close to being introduced in other states, neighboring states, and it's also percolated down into the local level, local government level. And just to close, all of this has happened, and we have many other things that are on the horizon, with basically about 40 active volunteers, no paid staff, no formal legal status, either as a nonprofit or as an LLC, and not a single dollar has been raised or granted to support this effort. It all comes from the creativity and the contribution of our small but growing community. And we just use a bunch of free stuff. We hang out on Discord, we use Google Drive, we communicate on Zoom, increasingly we use YouTube and Twitter, and we use Trello. So it's all free stuff. And that, more or less shows at this stage, we think that there's a bright future for the ability of networks of people to grow creatively and to have a significant impact on DAC's future. Thanks so much.
All right. Thank you, Chris. And for those professors in the audience, for students in the audience, I strongly suggest you check out that Violet system. I think it's something you might want to build at your institutes. So with that, we're going to move to a Q&A and panel discussion component of our event. I'm sorry, I just got windows popping up in my face. So I'll start us off with one question. There's been a lot of interest from our audience about Kristen's comments around 50% of the negative emissions aren't actually net removed from the atmosphere. So I'm hoping if you could clarify that. Let's say I have so many negative emissions from the soil system or from a direct air capture machine. And that's, what are the outcomes there?
Yeah, happy to clarify that. I think that is a common misunderstanding. So I find it easiest by drawing on the analogy with positive emissions. So that's what I tried to do, but I had to go over it very quickly. So so if we emit a given amount of carbon dioxide into the atmosphere, then because of what is called the CO2 fertilization effect, so the fact that plants are more productive in an enriched atmosphere, and because the flux of carbon dioxide into the ocean depends on the difference in carbon dioxide between the atmosphere and the ocean, part of that emitted CO2 ends up in the biosphere and in the ocean. And historically, it's been about 50%. So if we emit a ton into the atmosphere, about half of that has ended up partitioned between the ocean and the land, and about half of it stayed in the atmosphere. So now there's some variability around that, because sometimes there's drought in Indonesia, and so the proportion that the biosphere takes up carbon changes from year to year, but roughly it's been at 50% over the last few decades. So now when we remove carbon dioxide, then we have to sort of to think of this in reverse. And I think it is most helpful to think of a reference situation where we do not remove that carbon from the atmosphere. So in that case, we would have higher atmospheric CO2 concentration. But then if we, let's say, if we sequester carbon dioxide in the soil, or with direct air capture, we're removing some of that carbon dioxide from the atmosphere. And now actually the ocean sees a lower carbon dioxide concentration, and so it will return some of that carbon that it absorbed when it was emitted back into the atmosphere. And for the biosphere now, because the CO2 concentration compared to that reference case is also lower, we'll see a reduced CO2 fertilization effect, and so we'll actually absorb less and leave more into the atmosphere. And then again, under these same conditions, if we, let's say, remove 1 ton with direct air capture, then this would only result in a 0.5 ton removal from the atmosphere.
So we can see that there's a tall order in what we're going to be needing to remove from the atmosphere.
And so maybe just to clarify this, so that it makes sense, right? Because otherwise we would have if the goal is to offset emissions with removals, right? And if emissions end up, or 50% of the emission ends up in the land and the ocean, and that 50% weren't returned if we remove CO2 from the atmosphere, then actually we wouldn't have carbon neutrality by offsetting an emission with the same amount of removal, but it would somehow magically remove CO2 from the atmosphere, right? So that should make it clear that these are compensating mechanisms, and the removal has the same Earth system processes work in reverse. And while they work in favor of emissions, they work to our detriment in the case of removal.
Okay. Another popular question that has come up, or theme from our audience, is on the deployment of nets, on kind of the engineering and the upscaling of that. So one argument here is, do we just need to throw more money at the problem? Are we facing an engineering or a technical limitation, or are we facing a limitation on, say, political or social will? And perhaps Jen, might I pick on you to comment on perhaps the engineering side, and Holly or Christopher to pick up on the social dynamic?
Sure, I can talk about this. Well, I mean, one thing I'm going to say is that technology is not the solution. Do we have the technology to fix some of these things? Yes, we have it. It exists. Commercial scale technology exists today to do carbon removal from the atmosphere with chemicals. But the issue is that today they're expensive. Will they always be expensive? Not if we actually learn by doing and increase the deployment. So it feels like a chicken and the egg a little bit, right? Because it's like, okay, well, how do we learn if we don't have the money to build? And so some of the projects that are getting going, like Climeworks, for instance, you have to think about other opportunities to make money with the CO2. If nobody's going to pay you to put it underground, like in more carb fix projects or dedicated geologic storage projects, then you need to turn the CO2 into something that, you know, can actually be sold into a product. And so some of their projects are looking at green hydrogen plus CO2 from direct air capture to fuels. And so they're partnering, for instance, they have a project where they're partnering with Sunfire to do the green hydrogen. And then there are already airlines that are interested, and airports that are already interested in purchasing and having that fuel made available. And so, but those are early adopters. And I think this goes into some of what Holly's presentation says too. And that is that you want it to be affordable for everybody. You want you want all of the airlines to be able to afford a fuel like that. But these types of things are very expensive today. And so those that are making pledges, like some of the big companies that you see, there's been like 110 pledges in the last 9 months of like getting to carbon neutrality and needing carbon removal to be part of that path. And so there are companies like, and we've seen them with Microsoft and Amazon and Stripe and Shopify that are making these pledges and are investing in these technologies. And that's great because it means that we'll get some of these projects off the ground. And I think that we will see a little bit, we'll realize some lower costs as we do that. But in the end, we need policy. We need effective policy to help close the economic gap. We need investments. And I always go back to 1966 when we invested a significant amount of GDP for science because we wanted to be the first ones in the United States. We wanted to be the first ones to get to the moon and safely back to Earth. And we were willing to invest for that. And we need to invest in this now in the same way and even more, but even that amount would be significant. So it's not science in itself, it's science coupled to effective policy.
Mm-hmm. So it sounds like we probably can't rely just on corporate goodwill, but we should leverage what there is there to help, bring the costs down. But, that maybe Holly, do you have something to say on that?
And just to add to what Jennifer said, I think that right now we obviously need to focus on it as an engineering problem and put a lot more resources into R&D, but at some point you actually have to place that idea on the ground, and the politics of infrastructure in North America are extremely challenging. These have some design in, and so I don't think of environmental justice as a secondary or later consideration. I think it has to be moving right along in parallel. And I do think that opinions and norms and thoughts about this can shift relatively quickly because of the social media ecosystem that we're in. So maybe it won't take a decade to build that support.
Yeah, I think one thing that's interesting to me is where we are right now. It was Marshall McLuhan who said that we always look at new technologies through the rear view window and frame it in terms of previous technologies. And I can't help but think that direct air capture in particular is framed in terms of power plants. It resembles in our imagination the source of the pollution. And I wonder if that will always be the case. I think we should liberate ourselves maybe from that form function. I think as a solar person who sees the sort of the magic of modularity, who's also dealt a lot around the same question, where you'll always get a map of, if we were to solarize our entire electricity grid, you'd have to cover up X percentage of New Mexico. Well, the reality is we don't have to do that. You can embed the technologies in things, and so I do wonder if, because of the constraints on environmental justice and siting, if you might see a trajectory for this technology that is actually smaller and more distributed rather than big and plant-like.
I think maybe we can take that idea and negative emissions, in particular the biological or natural approaches, involve a lot of land use constraints. There's also water and materials, and so we haven't touched on it too much. But would anyone like to talk about how these kinds of co-benefits and also costs can influence the portfolios that we might be seeing? I guess.
Can you just, sorry, clarify that?
Sure. Okay, so I guess definitely we want to, you gave a good example of, what if we paint New Mexico full of solar panels? But there are some hard constraints, say, for instance, if we are using a biological approach on just what's available as the available sunlight to drive a particular natural process. And so we might expect, we will need that area, but not necessarily concentrated for sure. There are economies of scale, though, at least say with agriculture, it tends to be the case with farms. So, are we going to expect that kind of consolidation of let's shift that then. Are we going to expect consolidation of negative emissions because of economies of scale, or can we support through appropriate policies something that is more local?
I mean, I would just add that, what Chris was talking about, if something is modular, it scales linearly. And so it's not that, oh, we need to get 1 million tons of removal and then it becomes cost effective. And so that's the beauty of modularity in my, opinion. And like, I like that concept, Chris, that you said of like imagining that, and I'm not just for direct air capture, but for solar, I can see that. And that makes a lot of sense. Maybe for direct air capture too, but it's like, especially, we do that a little bit for DAC with the waste heat. It's like, well, somebody else already built the infrastructure and there's waste heat. Let's use it for something good. Or, another example too is, stranded assets. If we are going to get to renewable, if we are going to get to renewables for electricity generation at a very increased rate, which means the retirement of some of the power plants early, some of the natural gas in the United States in particular, maybe they could be retrofit to do direct air capture because they're not a stranded asset if you do something like that with them. And so I think that there's a lot of flexibility in those types of things, and finding the synergies and finding the opportunities rather than going to like, the other thing I'll just say, and Devin, from what you said too, there were a few things mixed in there. And I think there's also a priority list, and this is probably a longer conversation and everybody might have a comment on it. But if you take land, you have to ask the question of what's that land best suited for? Is it best suited for growing trees? Is it best suited for solar panels? Is there a way to have synergy and do both? To use the land in the best way we can. The same goes for low carbon energy. If you have the opportunity of low carbon energy and there's a coal-fired power plant there, it should be used to displace the coal before anything, and certainly not used for direct air capture, even though that's ultimately what you would want to couple to direct air capture to energize it. But there's a priority, I think, in it, and I kind of call it responsible siting of carbon dioxide removal projects, where we have to think about that.
If I don't want to hog the clock, but if I could just add one other sort of corollary to the modularity piece, it's a technical question that gets around siting and all the things that we can predict right now. But a key thing about modularity and smallness is that it, just by its nature, allows us to do things quicker. And it also allows more people at the margins to do things with it. And as a solar person, I just cannot help but look at it through that lens, is that solar, the reason why I beat all projections on how fast it would grow is because it's just a simple square with no moving parts that somebody in Kenya or in rural India can be thinking creatively about how to use and deploy it, just as someone who's trying to build a power plant. So there's a real imagination, creativity question that goes along with smallness that might just produce trajectories that make all of these conversations we're having about siting less relevant than we think they will be in 10 years.
Sounds good. And I just want to take...
Okay, just sort of a very brief thought. So I really like this idea of modularity and smallness. So Chris, you applied or sort of you demonstrate this mostly for DAC. So I was wondering about some of these nature-based solutions, especially if we're thinking about soil fertility, so soil carbon sequestration, so at the plot, at the farm scale. So what I could also imagine is leveraging these networks of farmers. It seems to me that there is that there is potential for this, and yeah, I don't know if Chris has the time, but I'd be interested in hearing if there have been conversations around extending this idea to other nets.
I can just say briefly, that's not my area of expertise. I'm sort of a DAC focused person, but a couple of years ago, I did moderate a panel at Urban Green about soil sequestration within cities. And for me, again, there's such a focus on volume. We need to do volume right now, but there's such an interest in cities, at parks and other areas, to do interesting things, that while the scale potential might not be cities, some of the early innovation about how you maximize sequestration in small spaces might happen in cities. So, but again, I'll leave the floor to somebody who actually knows what they're talking about around biological solutions.
I'll just jump in here, and I want to thank all of our participants, our attendees. I'm being inundated with questions that we can't possibly all answer today, but I will invite you to send them my way after the event if we don't get to them. I will do my best to respond to them. All right. That said, I'd like to take an opportunity to bring in a bit of the British Columbia experience here, and it's also going to apply to also the United States, where a lot of our panelists are located. And, you know, in the Northern Hemisphere, we hear a lot about negative emissions driven by our forest sectors. You know, for example, afforestation, reforestation, or long-lived hardwood, you know, or wood forest products, BECCS. Kristen, I'd like to ask for your insights on that very briefly, but because I think, you know, there are questions about the capacities, but also the albedo effects that our audience might want to hear about.
Yeah, I can definitely address that. So maybe one distinction I'd like to make is so when we talk about nets, what we're really talking about is negative emission. So it is enhancing natural mechanisms in order to remove CO2 from the atmosphere, which is different than reducing land use emissions. So things like deforestation, forest degradation, release carbon dioxide into the atmosphere, and addressing those is also very important. So that should definitely be part of our mitigation portfolio, but is not what is considered as a net. So just to clarify that. So yes, there are. So when we're talking about reforestation, afforestation, we're talking about planting forests in areas that are currently do not have forest. And in the Northern Hemisphere, especially in regions that have snow cover, the albedo in winter changes dramatically depending on whether we have a bare or whether we have a grassy area, let's say sort of something with crops, or we have trees. So that's something that we know if we look at our mountain slopes where we have a forest, the mountain slopes are dark in winter, whereas if we have, let's say, a ski run or something like this, sort of they're white. So this really influences the reflectivity. And there have been some studies now for over a decade that actually show that the net climate benefit of afforestation in high latitudes is limited because of the albedo effect. So yes, we're removing carbon dioxide from the atmosphere, but on the other hand, we're also reducing the Earth's reflectivity. So this has to be pondered carefully.
Thank you. And I wanted to pick that example out in particular to reinforce the idea that we might want to be considering portfolios of solutions and not just try and look for that silver bullet, as often I hear sometimes natural solutions are presented as. On a similar note, thinking about building portfolios, it relates to the natural system. You know, even if we started now, negative emissions are going to require years before we actually get some big rates being drawn down. And that applies if, say, we're planting a forest, there's a scale up period. It matters if we are building direct air capture and sequestration plants, we need to make investments. Now, often we're talking about For instance, nationally determined contributions at 2030 scales, but these are really long-term problems. And, what are aspects of regulations or policies or incentives that, governments may have to, spur a development in negative emissions technologies, even though, there's this conflict between short-term goals and long-term goals. And in particular, one example is people are looking for money too. They're looking for intellectual property protections. Is that a hindrance or is that a help in driving innovation? So I give a lot of ideas there. So perhaps I'd ask maybe Holly or Jen to speak to that.
So the question is about the role of intellectual property today.
Well, let's say in general, the root question is, we have long-term big problems, but we're often fixated at short-term goals. And how can we make robust policies, and how can we fix policies that exist today that might not be good?
I'm hopeful that because we're seeing the direct effects of short-termism with the pandemic and other things, that I think it has to be a cultural shift, really. I don't know if I have more than that about looking at these longer time scales, but there's a huge role for education and just thinking about scale in general, and some of the scales that Kristen's presentation brought up about the carbon budget, for example. I think that goes along with this bigger thinking.
I can mention a couple things too, but Holly, you mentioned education, and it's like, I think that is so important. And I feel that, if we're really going to do this on the gigaton scale by mid-century, and we look at all of these companies and all these people trying to do it on still a small scale, the labor force, the workforce that's going to be required to be a part of that is going to be quite significant, which is wonderful because it results in lots of jobs. But at the same time, we also need really creative people that are helping, with, for instance, new ideas like R&D in the lab, and maybe that's academics, so more professors getting excited about working in this space. But we also need really, smart people who have a little bit of background in the space and understand the difference between carbon removal, avoided carbon, and the distinction between something that's just a reduction versus something that's an actual removal, and being able to understand that messaging. And that transcends to not just policymakers, but reporters and writers, and those are the folks that are really communicating to the broader audience, not the academics and the professors. And that's another type of education, because in the end, it's voting and having informed voting and decisions. And I think that all education has just got to be first and foremost in order to really make this all happen. But then what I was going to say, though, before all of that, is that in our Academy of Sciences report, our agenda for doing that was really to come up with the research landscape and what that might look like. And what, in the end, we realized that, sure, there's a lot of technologies, for instance, for mineralization or for direct air capture that are expensive today, but they're actually commercial technologies, and we need to increase them by 1,000 times. But it doesn't mean that that's the only technology that will work. So we still do need some R&D. And so, we essentially look at all of the funding organizations and the different levels and recognize that deployment was important. And in some cases, that's what needs to, that's where the funding needs to be. But at the same time, there still needs to be resources for creativity and new ideas, and doing some of the things that Chris talked about, for instance, with modularity and small scale.
Okay. So our ending time was scheduled for 1/2 but I think we do have the budget to add a few more minutes. I have one last question before we move to closing remarks, and we'll try and, I'll ask that if you want to reply, keep the answer short. But the idea of the actors, who's participating in these climate solutions. And the elephant in the room is that the large corporations with major carbon liabilities often have the smart people and the wherewithal to undertake big negative emission scale-up in projects. Is that just, you know, what can a just transition look like, you know? I'll just leave it there. I mean, I think a lot of people have a lot of things to say about that. You know, is it right that I'll use an example. Recent oil and gases have made pledges for net negative emissions. You know, are they just covering, hedging their bets? You know, is their effort genuine? If we trust their pledges, you know, is that even going to be enough to get us to where we want to be?
Hard to answer that concisely. I'll let others. I have a thought on it, but I guess just in brief, one thing I would say is sometimes we get really caught up in the moral battles between the good guys and the bad guys, and I get that. I've been doing climate stuff for 15 years. There are bad guys and there are bad actors in this. But in terms of what happens to the technology, it's just not as predictable. So if you, in the early phase, have interesting bedfellows who make big investments in, let's say, DAC early on, that can be transformative in terms of what DAC becomes and how it's liberated for other uses. So I don't know what the right answer is on that, but I feel like sometimes we have a bit of a static idea of the sort of the moral battlefield around this, that sometimes we can't see the main question of what's the number in the sky, what's the ppm, you know, we sort of lose sight of that. But anyway, I'll leave it there.
I think that, I mean, I don't have the answer, but a few considerations. Obviously, there's a lot of smart, creative, and good people within the oil and gas industry, but they're working within a structure in which they need, reserves on the books and all these other things to show profitability. And so they're constrained in what they can do. One answer is that, we should nationalize fossil fuel companies and turn them into carbon removal companies. It's a little bit complex because, I mean, most of the reserves, at least in the world, are already held by national oil companies, not private oil companies. So then, I mean, are they in a better situation to make this transformation? I don't know. I think Aramco is doing interesting things, at least rhetorically. I don't know how that's going to end up in the end. So I think the question of the role for oil and gas is really hard. But I think that, I mean, this is a crisis, and if there's any time to start doing more planning and consciously phasing out industries, there's no better rationale than like a 4 degrees world looming to do it. And there's plenty of other industries that we need to think about phasing out as well. I don't know, single-use plastics, for example. Okay. So maybe we need a broader societal model about how to direct the futures of different industries than we have right now.
Now, I unfortunately, we are kind of coming to the closing part of our event today. And so I'd like to give each of our panelists a moment to kind of formulate some closing thoughts. And we'll do that in the same order as originally presenting. So if I could ask Kirsten, could you please share a few thoughts? And we're going to try and keep everybody's contributions, say, 2 to 3 minutes. Otherwise, we'll be here for quite a bit longer.
Okay, thanks, Devin. So I think these nets show some promise, especially those that have co-benefits in other areas in terms of biodiversity, in terms of clean air, clean water. Some also have co-benefits for sustainable development goals in terms of food productions. So I think these are interesting. What worries me is that this sort of whole, or that the focus on net is going to detract us from the work at hand, which is really to decarbonize our economy. So I think that has to remain the first priority. But sort of we've heard a lot about R&D, about investment, and my worry is that if we sort of open up this field, that somehow these resources are going to move away from mitigation, which in my view should be our foremost priority. And then maybe as a second thought is that so right now when we look at all of these reports, we see these CO2 sequestration potentials as sort of the measure for effectiveness. And so I think we need so before we start deployment, we really need to understand what some of the Earth systems feedbacks are, because actually so sort of deployment of some of these things at large scale in the wrong location could actually in terms of climate benefits, which is the sort of the whole purpose of all of this, could actually lead us to worse place than where we are. So we really have to do this in a very considerate way and really understand what some of the feedbacks are.
Mm-hmm.
Good,
Thank you. And Jen?
Sure. I would say, I'll emphasize that we need everything. So deep decarbonization and carbon removal. But I think my party message would be that we need to be thoughtful. Citing of the various types of projects, I don't think is given enough consideration. Regionally, the solutions or the options for carbon removal are quite distinct. And I think it's really important in one given location to recognize what are the low carbon energy resources, what is the culture of the environment. For instance, building a DAC plant coupled to geologic storage looks a lot different in the state of Texas versus the state of California. And I think that it's important to recognize and not force solutions, but really look at the stakeholders and the people on the ground that are actually going to have to implement these changes and maybe even modify their lifestyles to try and minimize what those barriers might look like for them. And but at the same time, do our best to try and just have deployment increase so that we can meet our climate goals ultimately.
Holly?
I guess the last thing I would add is that while we're figuring out how to phase out a planetary scale industry that's caught up in the everyday lives of people as well as the revenues of national governments, we could think more about this idea of a carbon take-back requirement. There's been some good writing on it. Basically, the idea that a company that produces a ton also has to take back a ton could be a good starting place, and I encourage you all to look into it.
That seems like that might come in, and that relates to Kirsten's earlier observation about the point at which we flip between every ton out must come back if we are to stay within our budget. And lastly, Chris?
Yeah, I think I spoke the most, so I'll be brief, but I think just to reemphasize on just as a solar person, just the significance of getting things out into the world in any kind of way, in any sort of form, is so key to the creative life and future of that technology. And so much is so speculative when we haven't had really much deployments yet. And I just take the example of the computer. Computing was thought to be in the post-war period these giant underground fortresses that people with lab coats would walk around. They're exclusive and huge by nature. And it was a bunch of nerds, basically, volunteers, that conceived of the idea of the personal computer. And that became the dominant paradigm. But it just required getting it out into the world. And I think we should expect to see that with DAC and other nets as well.
All right. And, oops, I'm sorry. Yeah, okay, you can all see me and hear me. So don't leave yet. Firstly, I'd like to thank our panelists for joining us today and sharing their expertise. I also want to thank the audience for their participation and interesting questions. I know that we didn't get all the questions answered. I invite you to please reach out to me, and I can help you get answers to that. It's also a challenge when dealing, with the topic in such a broad sense that we can't drill into every specific detail as very interesting as it would be because of limited time. Last note, I'd just like to point everybody towards signing up for the PICS mailing list. It's the best way to stay up to date on our funding opportunities, research, and events. And with that, I would like to bring our event to a close. I